Let's talk about piezoresistive sensing today. So the first thing I want to introduce you guys to is the piezoresistive effect. So the piezoresistive effect describes how the resistance of an object changes when the object undergoes a mechanical deformation. So for example, if we have a simple beam structure like we've looked at multiple times in this class, so something akin to this, where this is our original length. And this is our original cross-sectional area. If we were to essentially pull on this beam, we would expect to see that the cross-sectional area will get slightly smaller while the length of the material would increase. So something akin to this. Right. So smaller area, longer length, where this change in length is being vastly exaggerated for the overwhelming majority of materials. So if we were to assume that current is flowing in the longitudinal direction in this device, or in this beam here, its resistance, R, could be expressed as the electrical resistivity, rho E, multiplied by the length over the cross-sectional area. Okay. So under this mechanical deformation, the length is changing, the cross-sectional area is changing, and the resistivity of the material will also actually change because its resistivity is dependent on the internal atomic positions. And as we deform that material, those internal atomic positions are going to change slightly. Okay. So from this, we would observe a fractional change in resistance. Okay. So the fractional change in resistance of the beam is given by the relationship delta R over R. So this is simply the change of the resistance over the nominal resistance value before the change is going to be equal to the change in resistivity or really the fractional change in resistivity, minus the fractional change in the area, plus the fractional change in the length. Okay. So this first term is due to material properties. And the second two terms are due to the geometry of the system. Okay. We are going to define a piezo resistance coefficient. So let's say that the piezo resistance coefficient we're going to use pi, and it'll typically have some subscripts on it as well, and we'll introduce those here in a moment, is the fractional change in resistivity per unit stress. Or mathematically, pi will be equal to delta rho E over rho E divided by our stress T. And we could also express that as delta rho E over rho E divided by Young's modulus times strain, okay? So this equation looks fairly straightforward. However, piezoresistivity is an anisotropic property, meaning that the directions are very, very important, okay? Another important figure of merit that's used to characterize the piezoresistive effect is what's called the gauge factor, okay? So let's say that the gauge factor GF is the fractional change in resistance. Goodness. Per unit strain. And mathematically, we have the relationships delta R over R divided by delta L over L, since delta L over L is simply strain. So that would actually wind up looking like 1 minus the change in, or fractional change in area divided by the fractional change in length plus fractional change in resistivity over the fractional change in length. And this can be written as 1 plus twice nu plus E times our piezoresistive coefficient. And this nu, just to remind you guys, is the Poisson's ratio that we introduced much earlier when we were reviewing mechanical concepts. So the first two terms in this expression for the gauge factor is due to any geometrical changes that our material experiences. And then the Young's modulus times piezoresistive coefficient term E pi is due to the changes in the material properties. So since Poisson's ratio is relatively low for almost all materials, so somewhere between 0 and 0.5, the effects of the geometric changes on the gauge factor usually ranges from 1 to 2. And any gauge factor that's larger than this means that the change in resistance is primarily due to the material properties, okay? So let me just kind of write all that bit out. So for most materials, zero is less than, nu is less than 0.5. So the geometric changes on the gauge factor, and we're just going to write GF here, range from 1 to 2. Any gauge factor larger than this means that the change in resistance is primarily due to material effects. In other words, we could say that our gauge factor is going to be approximately equal to Young's modulus times our piezoresistive coefficient. Okay. So I'm going to give you guys here a brief table containing several materials that are used in both macroscopic and microscopic strain gauges and things like that, as well as their associated gauge factor. So aluminum has a gauge factor of 1.4, relatively low, right? Copper has a gauge factor of 2.1, also still relatively low. Platinum has a gauge factor of 2.6. Okay. Nickel has a gauge factor of negative 12.62. Okay. So that's a pretty appreciable gauge factor. Okay. So this is the reason why nickel is the most commonly used material for macroscopic strain gauges. So if you want to go buy a load cell or something like that off of McMaster-Carr, Mauser, or DigiKey, you'd typically buy a nickel strain gauge. That's literally what they're called. If you guys did your undergraduate here, you probably dealt with nickel strain gauges in your statics class. Okay. Getting into materials that we might use for MEMS devices, polycrystalline silicon, which I'm just going to abbreviate as poly-Si, has a gauge factor ranging anywhere between negative 30 up to positive 40, depending on what crystal direction we're looking at. So that is a pretty damn huge gauge factor. And then single crystal silicon, gauge factor ranges anywhere from negative 102 to positive 135, depending on direction. So the large gauge factors of silicon in both a polycrystalline and single crystalline form makes this material extremely attractive for use in piezoresistive sensing because we see a relatively large change in resistance due to a small applied strain. Okay. So I'm going to give you guys a moment to catch up because you usually tell me I'm going too damn fast before I go to the next page and start writing more shit down. Drew, let me know when you're done.
Good now.
Okay. All right. Shake out your hand and get ready. So let's talk about the piezo-resistive properties of silicon. So the piezo-resistive properties of silicon can be essentially quantified in a large matrix, okay? Where, let me write this out. So in the case of crystalline silicon, if the X, Y, and Z directions are aligned with the 100 family of crystal planes. I guess before I go off too far on this, I want to make sure that you guys know what crystal planes are. Are you guys aware of crystal planes and crystallography and all of that kind of good stuff? Yeah, so Miller indices, right? So the 100 family of planes would be if we were looking at a unit cell, we're just looking at the faces of the cube, right? And then the 110 family of planes is the one that cuts across the diagonal, and the 111 family of planes is the one that's tilted back to make that triangular shape, okay? So if we line up the X, Y, and Z axes with the directions of a cube, okay, then we can get a relationship between resistivity and stress, okay? So I'm going to draw a matrix here. So I'm going to have delta rho 1 over rho naught, delta rho 2 over rho naught, delta rho 3 over rho naught, delta rho 4 over rho naught, delta rho 5 over rho naught, and then lastly down here, delta rho 6 over rho naught. I'll explain what all these directions and all of that kind of stuff mean in just a moment. So this is going to be equal to a matrix of piezo-resistive coefficients. So this guy is going to be a 6 by 6 matrix. So pi 1, 1, pi 1, 2, pi 1, 2, 0, 0, 0. Pi 1, 2, pi 1, 1, pi 1, 2, 0, 0, 0. Here we've got pi 1, 2, pi 1, 2, pi 1, 1, 0, 0, 0. Oops. I need to draw this better so that these line up. Sorry about that. Here I'm going to have 0, 0, 0, pi 4, 4, 0, 0. And it's just going to be pi 4, 4s on this diagonal from here on out, if you're faster than me in writing this out. So these piezo-resistive coefficients multiplied by stresses T1, T2, T3, T4, T5, and T6. And over here on the right is where I'm going to introduce information about our directions here so that all of this kind of makes some amount of sense. So T1 is our stress in the X direction, T2, Y direction, T3, Z direction. These are our three normal stress. And then T4 through 6 will be our shear stress. So we'll have YZ, XZ, and XY. So where rho sub naught is the isotropic resistivity of the unstressed crystal. And the pi ij piezoresistivity coefficients are the components of the piezoresistance tensor. So from this relationship, which we're practically never actually going to use for anything, we're going to simplify this down because we're engineers, not physicists, thank goodness, okay? We can see that there are really only a handful of different coefficients, right? So we've got a pi 1, a pi 1, and a pi 4. These coefficients aren't constant, but they are influenced by the doping concentration, doping type, and temperature, okay? So in order to simplify this stuff down, we're going to hit you with yet another table here. So these are going to be our piezoresistive coefficients for silicon, single crystal silicon at room temperature. Okay. So in this column, I'm going to have our coefficients. All of these are going to be units of 10 to the negative 11 per Pascal. And then here, I'm going to have a column for N-type where the resistivity of N-type will be taken to be 11.7 ohm centimeters. And then over here to the right, this will be valid for P-type, having a resistivity of 7.8 ohm centimeters. And just to be clear, these values are valid at T is equal to 300 degrees Kelvin, so room temperature, and they're only valid for NA or ND is less than 10 to the 17 per cubic centimeters. So for the EE folks in here, I would interpret that to be if we have P-type silicon or N-type silicon, we can use these. But if we have P plus or P plus plus or N plus or N plus plus, meaning not super heavily doped, these are valid, okay? But if it's really heavily doped, we can't use these numbers, okay? So our value for the pi11 coefficient is going to be negative 102.2 for n-type and positive 6.6 for p-type. For the pi12 coefficient, we'll have a value of 53.4 for n-type and negative 1.1 for p-type. And then lastly, for pi44, we'll have negative 13.6 for n-type and positive 138.1 for n-type. There's going to be for p-type. Okay. And now I'm about to hit you with yet another table. Okay. So this is just what's going to tell us how to use these coefficients depending on the direction of the crystal that we actually have. Okay. So this one's a little bit more simple. Okay. So when strains occur in directions other than the 1, 0, 0 directions, we use combinations of the anisotropic piezoresistive coefficients. Yep. So this table is going to have 4 columns. We're going to have the direction of strain in the leftmost column, the direction of current in the left middle column. We're just going to label the configuration here in this right middle column. And then lastly, over here to the far right, we're going to have which piezoresistive coefficient to use, or combination of them to use. Oh, I didn't want an arrow. So when our strain is in the 1, 0, 0 direction and our current is flowing in a 1, 0, 0 direction, we have a longitudinal configuration, and we simply use the pi11 coefficient. When our strain is in the 1, 0, 0 direction and our current is in the 0, 1, 0 direction, so that's 90 degrees orthogonal, we are in a transverse configuration, and we use the pi12 coefficient. When our strain is in the 1, 1, 0 and our current is in the 1, 1, 0, this is another longitudinal configuration, but we're no longer directly aligned with our 1, 0, 0 family of planes. So we're going to use a combination here. So this is going to be 1/2 of pi 1, 1 plus pi 1, 2 plus pi 4, 4. When our strain is in a 1, 1, 0 direction and our current is in a 1, 1 with a bar over it, 0, meaning orthogonal to the 1, 1, 0 direction, we again have a transverse configuration. And we're going to use a piezo-resistive coefficient of 1/2 pi 1, 1 plus pi 1, 2 minus pi 4, 4. And then lastly, if our strain is in the 1, 1, 1 direction and our current is in the 1, 1, 1 direction, we again have a longitudinal configuration, and we're going to use 1/2 times pi 1, 1 plus twice pi 1, 2 plus twice pi 4, 4. Give you guys a moment to catch up on this before I.
Under the direction of current, is that supposed to be a bar over that one?
Correct. So what that bar is indicating here, so with 1, 0, 0 here and 0, 1, 0 here, we're essentially saying that the current is flowing 90 degrees perpendicular to the length direction. With these 1, 1 zeros here, it's a little bit harder to figure that out. So this bar is essentially telling us we're still just flowing 90 degrees perpendicular to the longitudinal direction of our device. Yeah. So, all right, so the gauge factor can then be determined by multiplying the piezo-resistive coefficient with Young's modulus in the direction of applied strain or GF will be approximately equal to pi times E, such that the fractional change in resistance is given by, I'm going to scroll down here. Let me know if I need to scroll back up, but I'm trying to leave enough on the screen where you guys can see what's what. Delta R over R will be a combination of the longitudinal change in resistance plus the transverse change in resistance. And we can kind of break this down a little bit further by saying that this is our longitudinal gauge factor. times our longitudinal strain plus our transverse gauge factor times our transverse strain, or our longitudinal piezoresistive coefficient times our longitudinal stress plus our transverse piezoresistive coefficient times our transverse stress. I'll give you guys a moment to catch up, and then we'll work an example problem illustrating how to use this. Okay. So consider the following microstructure here. I've got essentially an anchor point over here on the left-hand side of the page. And then I'm going to have a cantilever beam sticking out like so. And then there's going to be a proof mass attached to the end of that cantilever beam. So let's say that this length is 200 microns. The width of our beam is 20 microns. For our proof mass, this is going to be, I didn't draw it this way because I'm just shitty at drawing, but it's supposed to be a square. 50 micron by 50 micron, like so. And the thickness of this structure is 5 microns. So let's say that there were two piezo resistors integrated into this system. Okay, so let's put one right here, one right here. Like so. I'll give us our piezo resistor dimensions here really quickly. So let's say that the length of each of these piezo resistors is 20 microns. The width is 5 microns. And the thickness is half a micron. We'll say that we're using specifically 100 N-type single crystal silicon that has an electrical resistivity of 11.7 ohm centimeters. Okay. And we're going to be applying a force directed into the page so that we're trying to cause this beam to deflect into the page. And I want us to figure out from this what is the fractional change in resistance caused by, hey, F is equal to 25 micronewton force acting on the center of the proof mass. And then we'll follow this up with what is the absolute change in resistance caused by this force. All right. So in this particular example, excuse me, the piezo resistors are integrated at the anchor point. Anybody think about why we might have chosen to do that?
Is everything else suspended? Like
I mean, yeah, everything else is suspended. It's probably over some sort of substrate or something like that. But if you go back and you look at your notes for cantilever beam deflection, where does maximum stress occur? Maximum stress occurs at the anchor point. So we probably want to integrate our piezo resistors where maximum stress occurs, because that way we'll get the largest electrical signal out of them, right? So if we're doing this at the maximum stress point, we should see the maximum change in resistance. So if we had integrated it over here, we'd get practically no signal, right? So we want to place them in the points where we feel like they're going to see the most stress, okay? So talk about that a little bit more in a moment. For what it's worth, there's also a reason why the thickness of the piezo resistor here is 0.5 microns, where the thickness of the beam itself is 5 microns, right? So if we made our piezo resistor like incredibly thick, it's not going to deform easily. And if we had embedded it into the surface of the beam as opposed to depositing it on top of the beam, as we cross that halfway point, we know that our tensile stress starts to become compressive stress as this guy deflects. And so some of that signal is going to get canceled out. So realistically, we want our piezo resistors to be as thin as possible at the point of maximum stress. So that's what I've attempted to illustrate here. Okay. So going back to our notes from looking at cantilever beam deflection, we should be able to see that our maximum stress, Tmax, is given by the expression F times L times T over twice I, where, just to be clear here, L is the distance from the anchor point to where force is applied. F is the magnitude of the force, obviously T is the thickness. 2 is just the number 2. I is the moment of inertia, which was given by AB cubed over 12, where B is the direction of bending. Okay. So if I start plugging numbers into this thing, I've got my force of 25 micronewtons. My length here is going to be the entire length of the cantilever beam plus half of the length of my proof mass, because my force is applied at the center of the proof mass. So that's 200 plus 50 over 2, or 225. We all okay with that? Okay. So 225 micrometers. Our thickness is 5 micrometers. Then we're going to have a factor of 2 down here. And now I'm going to put in my I stuff. So A, so what do you guys think A is going to be here? If B is the direction of bending,
B do the thing.
so B is indeed the thickness. The 20 microns, so the width of the beam. Exactly right. Yep. So there's my AB cubed, and I've got 12 on the denominator of the denominator. So I'm just going to move that guy up here to the numerator, and this is what I get to put in my calculator. And when I put this into my calculator and do the unit conversions for you guys, I wound up getting 67.5 megapascals. Yay for MathCAD. I'm not doing this shit by hand. So we've got our stress. So if we want our fractional change of resistance and we know our stress, then really the only thing else we need to figure out is our pi longitudinal here. Okay. So yes,
The fractional change in resistance is delta R over R, right?
correct.
We just found strain
We found
T.
that. All right, so we're told here that our piezo resistor was created using the 110 crystal plane, and current is flowing down the long dimension of the piezo resistor. So if we come back up here, we're looking at this situation, right? Here's our direction of strain. Here's our direction of current. So this is the piezo resistive coefficient that we should be using. 1/2 pi 1 1 plus pi 1 2 plus pi 4 4. So pi L, or pi longitudinal in this case, said 1/2 pi 1 1 plus pi 1 2 plus pi 4 4. Substituting in our numbers, we're going to have negative 102.2 plus 53.4 plus negative 13.6. And then all of those numbers, if you refer back to the table, had units of 10 to the minus 11 per Pascal. And so simply throwing this into our calculator gives us a value of negative 31.2 times 10 to the minus 11 per Pascal. From this, our fractional change in resistance, delta R over R, is simply going to be our piezoresistive coefficient in the longitudinal direction times our maximum stress, right? So let me just circle back up here really quickly, right? So up here, I introduced the fact that our fractional change in resistance should be the sum of the change in resistance due to longitudinal plus the sum of the change in resistance due to any transverse. Well, in this case, we don't have any transverse stress at all because everything's just in the long direction. So that second term is going to go to zero. Okay. Yes.
Force was like, the first to have a transverse, part, of course, it'd be going, horizontal.
Yes, so we would have to have some component of our force trying to rotate this guy down. Okay. So since our force is directly into the plane of this, all it's doing is causing some form of tensile stress on these guys. It's trying to stretch these guys out, but it's not also trying to rotate them in any form. So it's not acting in this direction that would cause a transverse strain. So multiplying these two guys together, we'd have negative 31.2 times 10 to the minus 11 per Pascal times 67.5 megapascal. So that would be times 10 to the positive 6 pascals times 100% gives us a fractional change of negative 2.106%. So that 25 micronewton force causes our resistance to change by a little over 2%. If we wanted to calculate the absolute change in resistance, we simply multiply this fractional change in resistance by the nominal resistance of the piezoresistor, right? Which should be fairly easy to do because we have the electrical resistivity and its dimensions, okay? So the change in resistance is just going to be pi L times T max, which is our fractional change, times rho E L over A, which is just our nominal resistance. So that would look like negative 2.106% times 11.7 ohms times centimeters. The length of our piezo resistor was 20 microns. The cross-sectional area of our piezo resistor is the width of the piezo resistor times the thickness of the piezo resistor. So 5 times 0.5 microns. And this comes out to be negative 19, excuse me, 0.712 kiloohms. So for what it's worth, I did the math here so that you guys didn't have to. The nominal resistance of this guy is actually 936 kiloohms based on these dimensions. All right, we've got a couple more, I think, relatively short things that we can talk about real quick, and then we'll call it a day. One of them we've kind of already talked about, but I guess I'll draw a picture to kind of help explain things a little bit more. So placement of piezo-resistive sensors. So once again, dealing with kind of a cantilever beam situation. I'm going to draw kind of a side view thing here, right? So this is our anchor. And this right here would be representative of our beam. For, I believe, obvious reasons, we want to place our piezo-resistive sensors at the anchor point whenever possible, because that's the point that's going to experience the most stress and the most strain, right? So from there, we have two options. We can either deposit, or excuse me, we can dope our piezo resistor, meaning that it becomes part of the beam itself, which shouldn't be particularly difficult, because if we're starting with a semiconductor-based beam, right, we would just dope it as part of the manufacturing process, either through ion implantation, diffusion, etc., all of that kind of good stuff. We should be able to control the thickness through all of those parameters. Or the other option would be to deposit it on the surface of the beam. Right. So something akin to this. Both of these cases would be an example of a good design under the assumption that the piezo resistor thickness is small, so that the piezo resistor itself can largely be considered to be part of the beam, right? So what I mean by that specifically is if we contrasted, so let me just write here, good. And then let's contrast that with bad. Okay. So a bad doped piezo resistor design might be something like this. So there we've got our anchor. Here we've got our beam. And let's make our piezo resistor really thick. Okay. Why is that bad? And I'm going to pick on you because I haven't. You're shaking your head no. I guess I'm not going to pick on you.
It's not gonna like experience the same level of force that the smaller one?
Well, so what did we learn when we were trying to bend beams? the thicker it is, the harder it is to bend. So if we make that piezo resistor really thick, it's going to experience almost no deformation, right? So if we make the piezo resistor really thick when we deposit it on top there, it's going to generate practically no electrical signal because it isn't going to want to deform. It's too thick to be able to change dimensions, okay? And then a bad design for a doped piezo resistor. And we've already talked about this a little bit as well. So if my piezo resistor was so thick that it crossed over the neutral line of this, the top part of the piezo resistor is experiencing tensile stress. The bottom part is experiencing compressive stress. Those are in opposite directions, and so they tend to cancel each other out. So realistically, only, let's say, this part right here is actually doing anything. All of the rest of that is wasted material because the forces cancel out in a symmetrical region about the neutral line. And now I will denote this with bad. Okay, so now let's talk very briefly, and this will be the last thing that we're going to talk about today, temperature sensitivity, right? So the piezo-resistive coefficients are temperature-dependent quantities. So for doping concentrations, less than 10 to the 17 dopants per cubic centimeters, which is the value that we used as the constraint in our table for when it's valid. Okay. Piezo-resistive coefficients will change with temperature using the following simple relationship. So pi as a function of temperature is simply going to be our piezo-resistive coefficient at 300 K multiplied by 300 Kelvin over what our temperature is. So the hotter our system operates at, the lower our piezo-resistive coefficient is going to be. So this kind of limits the environments in which we can use piezo-resistive sensing to accurately measure things. Okay. I did the math here, but I don't know that we have time to actually go through it. Let me see. Okay. So let me just continue on with these notes here so I don't confuse myself too bad. All right. So this is how our piezo-resistive coefficient changes, right? Unfortunately, the resistivity of silicon is also dependent on temperature. For small temperature changes, around 300 Kelvin, silicon has a temperature coefficient of resistance of TCR1, where this one just means we're making a first order approximation because this is a very nonlinear effect here, of about 0.015 per Kelvin. Okay. And as it turns out, this effect can actually be greater than the piezoresistive effect itself. So I did the math for a 5-degree Kelvin temperature change and found that the temperature coefficient provided a 3.5 times greater change in the resistance than the piezoresistive coefficient. So this is one of the limitations with piezoresistive sensing, where we probably would actually, and I think I'll talk about this a little bit more on Friday. Sorry, I couldn't remember what day of the week it was. So when we implement these guys and we make piezoresistive measurements, what I did here, where I had two piezo resistors in series, we might do something like that, but we would probably also actually have another piezo resistor actually set somewhere inside the anchor point where it's not going to experience any type of deformation whatsoever, right? It's serving as a reference resistance. And the benefit of using a reference resistance in addition to our piezo resistor that's experiencing a change, they're both going to experience the exact same change in resistance due to temperature effects, which means those guys wind up canceling each other out. And the signal that we wind up measuring from that is only due to the actual stresses in our system. But we'll talk about that way more on Friday. All right, I've ranted at you guys enough, so enjoy your extra 30 seconds of life of not putting up with my bullshit. Thank you guys for your attention.